Hello again. In this lecture, we will talk about measuring mass, length, time, and force. When engineering calculations are performed, it is necessary to be concerned about the units. So mainly we have two types of dimensions. The first one is called primary dimensions, which are mainly the mass, the length, time, and force. So these dimensions are called primary since they are sufficient to derive and measure all other dimensions. So the other dimensions are called secondary dimensions. So we can write secondary dimensions in function of the primary dimensions, mass, length, time, and force. To talk about the units, we have two different systems. The SI units system, or abbreviation for International System of Units, International System of Units. And the second one is the English system, or English units. So now we will start by talking about the primary dimension units. So here we make a table for each quantity, how it is presented in SI units and in English units. So first, the mass in SI units, it's in kilogram and with the symbol kg, and in English units it's in pound mass, where we have the symbol lb subscript m. The second quantity is the length. In SI units it's in meters, it's the symbol m, and in English unit it's in foot with the symbol feet, ft. So the time is in second in S for both systems. For the English system is also in second S. For the force in SI units, it's in Newton, so the symbol N, and each Newton is, as you know, is 1 kilogram meter per second square. However, in English unit, the force is in pound force, or in a symbol lb with a subscript f, and each pound force is approximately equal to 32.2 pound mass feet per second square. So after we know about the units for the primary dimensions, it's important in engineering calculation to know about the conversion between different types of units. So it's important to know the following conversion in this course. So 1 foot, it is equal to 12 inch, and to give you an idea that 1 inch is approximately 2.54 centimeter, and 1 pound mass is equal to 0.45 kilogram, and also the important one is that 1 pound force is 32.2 pound mass feet per second square. So these are the important units. We will now go through, talk about the units of the specific volume. So now the specific volume. The specific volume, as we knew before, is the volume over mass. So in SI, it will be in meter cube per kilogram. However, in English system, it will be in feet cube per pound mass, or sometimes an inch cube over pound mass. So this is a specific volume on a mass basis. Sometimes we write the specific volume on molar basis. So on molar basis, we denote this by V, small v bar is the volume over the number of mole, where n is the number of moles. So in SI, n is in kilomole or moles, and in English system is in pound mole. So there is a conversion factor between the specific volume on a mass basis and the specific volume on a molar basis, which is the specific volume V bar on a molar basis is equal to the specific volume on a mass basis into the molar mass, or the molecular weight. So M is the molecular weight, and the molecular weight in SI units is in kilogram per kilomole. So every kilomole, how many kilograms it has. In English unit, it's pound mass per pound mole. So to derive this equation, V bar, V into molar mass, we can simply divide V bar over specific volume, V. So V bar is V over number of moles, and specific volume on a mass basis over mass. So V and V cancels out, so we are left with M over N. We all know that the number of moles is related to the mass and the molar mass by the following equation. So M over N is the molar mass. If we substitute this here, it will be equal to the molar mass. So we will end up with V bar is equal to V into molar mass. So that's it for the specific volume. Now we will talk about the pressure property. So the pressure, we all know that pressure is the force per unit area. So P will be in Newton per meter square. So this Newton per meter square will be equivalent to 1 Pascal. So 1 Newton per meter square, the force per area, is equal to 1 Pascal. 1 kilopascal will be equal to 10 to power 3 Pascal. 1 bar will be equal to 10 to power 5. So bar is also a unit for pressure and is equal to 10 to power 5 Pascal, or 10 to power 5 Newton per meter square, or you can say 10 to power 2 kilopascal. Also, we can express the pressure in megapascal. So 1 megapascal is 10 to power 6 Pascal and is equal to 10 bar. In order to measure the pressure, so pressure measurement, how the pressure is measured, pressure measurement. First, we will talk about the barometer. A barometer. A barometer is a device to measure the atmospheric pressure. It is a container with mercury in it and a tube, an inverted tube, which has a level of mercury, let's say here L, and in this, above the mercury, we have mercury vapor in vapor form, and this is mercury in liquid form. So if you know that the hydrostatic pressure distribution in a fluid is the same when we have the same levels, or if we take 2 points A and B, they both have the same level and they both correspond to the same fluid. So two conditions, two important conditions. They both should correspond to the same fluid. In this case, A correspond to mercury and B correspond to mercury. And the same level, the elevation of A is the same as the elevation of B. So giving these two constraints, we can say that PA, the pressure at A, is equal to the pressure at B. Here, on the mercury surface, we have an atmospheric pressure distribution. So PA is P atmospheric and is equal to PB, and PB will be equal to rho into G into L. You know that the hydrostatic pressure distribution is the weight per unit area above the point B. So PB equal rho GL, which is correspond to the weight of the liquid above this point. So, and plus the pressure of the vapor. So all the column of a fluid above B, which is here, is the mercury liquid and plus the vapor part. So since the weight of the vapor is negligible, we can neglect this term. P vapor is almost zero when compared to the liquid mercury. So you know the density mainly of liquids is much higher than the density of vapor. So we can approximate that Pb, which is equal to the P atmospheric, is equal to rho of mercury into G into L. If we take the example that the atmospheric pressure is equal to 101,325 Pascal, then this will give us a length of P atmospheric over rho into G. And we take here that the density for mercury is approximately 13,590 kilogram per meter cube. So is equal to 101,325 over 13590, which will be equal to 0.76 meter mercury. So we refer to mercury as Hg. So this is also a unit for the atmospheric pressure. So we can say that 1 atmosphere is equal to 101,325 Pascal and is equal to 760 millimeter Hg. In English unit, it is equal to 14.7 pound force per inch square. And in Hg, it will be equal to 29.92 inch Hg. So here we have shown how the barometer, using the barometer, we can measure the atmospheric pressure. To measure the pressure inside a tank, we use the manometer. So manometer, we can measure also pressure distribution. Suppose we have a tank and so this is a tank filled with some gas at a pressure P. So this tank, for example, let's say, so this tank is connected to a manometer. So mainly the manometer is filled with some liquid here. So here we have the manometer liquid. It could be water, it could be mercury, whatever liquid. And as we did before, to know the pressure inside the tank, we take 2 points at the same level and at the same, for the same fluid. Let's say point A and B. In the manometer, we can read this distance L. So let's say PA is the pressure of the gas. So this PA, since it is connected directly to the tank, so this is the gas pressure. So if we say that the PA is equal to PB, since same level and same fluid, you can easily say that the gas pressure, PA or P gas, is equal to PB. So what is above PB? We have rho G L plus the atmospheric pressure. So we have two pressure. One is due to the manometer liquid column above point B plus the atmospheric pressure exerted on the manometer opening. So in this way we can calculate P gas. We know L, we read it using the manometer, and we know the manometer liquid type, and we know its density, and we know the atmospheric pressure, so we can calculate P gas. In addition, it's important to know that we have different terminology for pressure. Sometimes we say the P absolute pressure. We say P gauge pressure, the gauge pressure, and the vacuum pressure. So to understand what this terminology means, let's take here a reference pressure equal to 0. So this is a reference pressure. So this is the absolute zero pressure. And here we have the atmospheric pressure, P atmosphere. And let's take a case where you have an absolute pressure which is, as you can see, higher than the atmospheric pressure. So the absolute pressure is always measured from the zero reference. Okay? So here, this magnitude between the absolute and the atmospheric is called the gauge pressure, P gauge, and is equal to P absolute minus P atmospheric. Another case, if we have the absolute pressure lower than the atmospheric pressure, so this is the absolute, this magnitude here is called the vacuum pressure, P vacuum, which is equal to P atmospheric minus P absolute. So these are different terminologies, but they just mean the same pressure. For example, if we have a case where P atmospheric is equal to 100 kilopascal, and let's say P absolute is equal here to 120 kilopascal. So this will correspond to a gauge pressure which is equal 120 minus 100, which is 20 kilopascal, which is only mean that if we say we have a gauge pressure equal to 20 kilopascal, that we are above the atmospheric pressure by an amount equal to 20. So, another case, suppose we have the absolute pressure equal to 80 kilopascal. So if we calculate the gauge here, it will be absolute minus atmospheric, so minus 20 kilopascal. So the minus sign will indicate that we are below the atmospheric pressure by a value equal to 20 kilopascal, that we are in some kind of vacuum. So that's why it is of interest to calculate here the vacuum pressure. So the vacuum pressure will be equal to the atmospheric minus the absolute, 20 kilopascal. So a vacuum pressure of 20 kilopascal just means that we are below the atmospheric pressure by a value of 20 kilopascal. Now we will move on to the temperature. In this section, the temperature measurement, for temperature measurement and units, we have two scales, the Kelvin and Rankine scales. For the Kelvin scale, we should know that the Kelvin temperature is equal to the degree Celsius temperature plus a factor of 273.15. So if we say like the temperature is 20 degrees C in Kelvin, it is 20 plus 273 is 293.15 Kelvin. Moreover, if we talk about the Rankine scale, T in degree Rankine equal to T in degree Fahrenheit plus 460. So let's say we have T in degree Fahrenheit is 100 degree Fahrenheit, for example. So it will correspond to a degree Rankine of 560 degree Rankine. So it is important in this section to know about, since we're talking about temperature, to know about the thermal equilibrium concept. If we have, let's say, for example, two objects, A and B, and suppose the object A is initially at some temperature, TAI, and the object B is initially at a temperature, TBI. And initially, TAI is larger than TBI. So object A is the hot object and object B is the cold object. If we connect the two objects by some conducting material, TA and TB, and we isolate the two objects from the surrounding, so they are not allowed to exchange of any type of energy with the surrounding, so this is an isolated system, and so heat transfer will start to occur between object A and B from the hot object. So heat transfer will always be from the hotter object to the cold object. Finally, this process will end when we reach thermal equilibrium. The thermal equilibrium is when the two objects are at the same temperature. So TA final, so the temperature of the object A will start to decrease, whereas the temperature of object B will start to increase until both objects will reach some equilibrium temperature. So the final temperature of A will be equal to the final temperature of B, and heat transfer will cease to occur since they are both at the same temperature. So we say that object A is in thermal equilibrium with object B. So based on this concept, we talk about the zeroth law of thermodynamics. The zeroth law of thermodynamics. The zeroth law of thermodynamics says that if an object A is in thermal equilibrium with an object B, and if an object A is in thermal equilibrium with another object C, that means that B should be in thermal equilibrium with object C. So suppose, for example, we have object A here, and we measure this object temperature using some thermometer. And so the thermometer and the object A will be in thermal equilibrium. They will both have the same temperature. And if we take, so here, if here the thermometer temperature is equal to TA, and if we take another object B and we measure it using a thermometer, the same thermometer, and it happens to be that it gives us, the thermometer gives us the same temperature as in the first case. So T thermo will be equal to TB, and this T thermo in the first case is equal to T thermo in the thermometer in the second case. So we can say that TA in this case is equal to TB. So that's the application of the zeroth law of thermodynamics. So now we finish this chapter, and in the next video we'll start by solving examples and problems. So see you in my next video.